Welcome, everyone, to today's discussion on municipal and industrial wastewater reuse. During the presentation, you'll learn about the needs and challenges that often drive reuse of wastewaters, as well as some of the typical solutions that are employed. Water is a finite resource, and factors such as population growth, regional drought conditions, as well as industrial production demands are driving an increased need to reuse wastewaters rather than simple discharge. We've separated the discussion between industrial reuse and municipal reuse, as there are differences in how you treat and reuse the wastewaters generated in those markets. Please turn to slide 2. Before we begin our discussion on wastewater reuse, it's important to understand the circularity of water use. Water for either market typically can be drawn from a variety of sources. It could be seawater, brackish water sources, such as what's found in estuaries on the coasts, surface waters, such as lakes and rivers, or groundwater, which is usually drawn from wells. These waters typically are initially treated for their specific use, either potable for drinking or as plant water for production needs. Wastewater generated from municipal uses is directed to a municipal treatment facility, which treats the water and discharges it, ready to start the cycle again. Industrial wastewaters are generally treated for discharge, whether that be to a municipal treatment facility for further treatment or directly back to a river, lake, or other location. Either way, water is used again and again, and organizations are exploring methods to get as much as they can out of every gallon they use. Please turn to slide 3. What is wastewater reuse? Specifically, reuse is taking water that was used in one process and repurposing it for use in another. Just for clarity, this is a little different than water recycle, where the wastewater is reused right back into the same process from where it came. Wastewater can come from a variety of locations. It may be from inside or outside the facility. As an example, some industrial plants are taking wastewater directly from a municipal treatment plant and using it as their supply water. In the end, the economics of the reuse application is often the driving force. So many facilities are exploring ways to recover costs by capturing energy or other valuable components in their wastewater stream. Now that you have a high level of overview of reuse, I'll turn it over to Alex, and he'll discuss wastewater reuse in the industrial market.
Thank you, Walt. Please turn to slide 5. Demand for clean water reaches across all industries: refining, chemical processing, food and beverage, mining, microelectronics, pharmaceutical, healthcare, data centers, and renewables, being biogas and biofuels. In these next few slides, I'll review some key factors of industrial water recovery and reuse and how it aligns with our core competency of delivering fully engineered, integrated solutions. Some takeaways from this section are going to be, firstly, the water plays a critical and integral role in the industrial processes. Next, there's a spectrum of market factors driving demand, including converging costs, as well as a firm sustainability component. And also that solutions are highly engineered and are typically assembled using a wide range of technologies. Please turn to slide 6. Water is critical to our customers' processes, as I said, and most notably as a heat transfer fluid. The water balance of an industrial facility is more accurately described as an energy balance. Water and steam are heat transfer fluids whose purpose is to extract, store, move, and inject energy, which directly impacts the cost and efficiency process. And therefore, management of the risk of that impact is a key component to water reuse. In contrast, water management and treatment are generally not core functions of most industrial facility owners. Outsourcing is already part of their business model, and they rely strongly on solution providers, including Evoqua, including us, to manage that risk, to design, build, and in many cases, operate and maintain the water systems. This is a central aspect of water recovery and reuse. That perceived risk is introduced when transitioning to recovered, treated wastewater sources. The transition may require infrastructure changes to accommodate water reuse, and in most cases, the solutions are site-specific and engineered to mitigate the risk. Please turn to slide 7. The cost of raw water is often less than water produced from reuse and recycling. These costs are converging, and in some regional cases, water costs have become a primary driver. But there's a number of factors which drive reuse projects. A holistic consideration is part of that evaluation process. Some factors: sustainability and environmental or social footprint plays a role, and increasingly so. Availability or scarcity of water for expansion for an existing facility or greenfield. Selecting a site for an industrial facility to be constructed or expanded is not made solely on proximity to adequate water supply. It's important, but it's certainly not a dominant factor. Seasonal drought and increasingly regional aridification impacts operations and plant throughput. Next, compliance with evolving or emerging regulations. It is often cost or design effective to include wastewater, to include water reuse and recycle either as a discharge management or a discharge avoidance strategy. Ultimately, we see all significant reuse projects being driven by the total economy of water. Successful reuse projects require a clear cost or performance advantage and well-defined return on investment. Please turn to slide 8. There's many potential sources of water within a facility to recover for reuse. Large volume flows, such as the final tertiary treated wastewater or the tailpipe, either intra-facility or from an adjacent municipal facility, and once through cooling or surface runoff are all examples of these large volume flows. Smaller volumes, but often easier to recover, point source streams include cooling towers, boiler, reverse osmosis brines, process condensate, process water streams, including strip sour water, for example, within a refinery, or whitewater purge sources within paper processing are typical examples of accessible streams for these point source treatments. Please turn to slide 9. The water treatment process required for reuse is driven by the gap in water quality between the recovered stream and that for the target reuse purpose. Treating the recovered water for reuse is a highly site-specific and source-specific, and the treatment strategy is determined by the target reuse water quality requirements. Solutions require highly engineered designs for an integrated system, and are typically assembled from a series of components intended to reduce and remove a number of contaminants. And sequentially, these might be removal of a free aqueous, non-aqueous phase from the water, removal of total suspended solids. Next, removal of residual organics or nutrients, nitrogen, phosphate, or maybe some other toxic components. And finally, the removal of total dissolved solids. And this sequential total design, all designed to meet the target treated effluent quality for use. Please turn to slide 10. Treatment cost per unit gallon is generally lower as volume flow increases. That and the practical need to recover large enough flows to significantly impact the water balance focuses many initiatives on tailpipe capture. However, treatment cost is only one factor. For example, moving water from point of recovery or treatment to point of reuse can significantly inflate project costs, particularly in brownfield. There are a number of site-specific factors that impact cost and practicality of reuse, and these include equipment footprint and availability of utilities at the source, at the point where the equipment is being installed, the location of reuse and volume demand. For example, localized capture, point source treatment and reuse of a small volume stream within an operating unit can still be cost effective despite higher unit volume treatment costs. The competing cost of piping in an alternate water supply inside an existing facility can be high, and thus comparing favorably to more remote tailpipe project. Please turn to slide 11. Each site, each initiative presents us with challenges to be addressed to achieve a value, cost-effective solution. The composition of the wastewater streams are dynamic, variable, and process-driven, driven by the process in the facility. The dog is always wagging the tail. Many of these initiatives are at existing facilities. These are driven by end of life service replacement, capacity expansion, process upgrades, evolving environmental regulations. And the reality is that the water recovery and reuse must be tailored, must be retrofitted onto a water and wastewater system that is old, tired, and often suffering from decades of underinvestment. Examples are, for example, individual wastewater streams within an industrial facility, which in themselves may be candidates for point source recovery and reuse, are often commingled in below-ground sewers, which are difficult and expensive to segregate. These systems are not amenable to standard bolt-on solutions. Other examples of the realities that reuse initiatives often collide with are gravity flow underground sewers. They're subject to minimum flow designs when they were originally built. Reduction of flows due to reuse initiatives can inadvertently reduce flows below what is required to flush these structures. Water treatment processes themselves may generate waste streams or concentrate waste streams, and the waste disposal fate impacts discharge compliance. Recovery and reuse must acknowledge the critical role that water plays as a heat transfer fluid in the heat balance of the process. The reality is that there are hard, defined limits to water use reduction with this limitation. Thank you, and I'll hand it back to Michael to expand on recovery reuse of municipal wastewaters. Michael?
Thank you, Alex. Good morning, everyone. Please turn to slide 13. For centuries, water has been used for cooking, cleaning, and conveying human waste out of homes into a waterway or other convenient disposal location. Domestic wastewater is full of bacteria, pathogens, organic material, and nutrients that promote algae growth. Left untreated, this wastewater is harmful to human health as well as to the environment. Cities have constructed wastewater treatment plants, also known as POTWs, publicly owned treatment works, to remove contaminants to prevent the spread of disease and the degradation of waterways. And traditionally, wastewater has been considered a hazard and a nuisance to be treated and discarded in the most cost-effective manner possible, with scarcely little thought about the value of its contents. Please turn to slide 14. There are numerous reasons why water recovery from wastewater and reuse is becoming a common practice. Among them are water treatment costs are rising rapidly. This increase in cost will be discussed in more depth later in this presentation. Water scarcity is becoming a bigger issue in many parts of the United States and around the world. Long-term drought has become especially problematic in the western and southern United States and may be driven by global warming trends. Regulatory challenges have caused increased wastewater treatment costs, but have also resulted in higher quality treated wastewater, which is more suitable for reuse. Sustainable practices to conserve water and reuse wastewater are becoming common, and there's increasing social pressure to do so. By recovering and reusing treated wastewater, load to the receiving stream is reduced, and flow-based processing limitations are more easily achieved as a result of the reduced wastewater discharge volume. Please turn now to slide 15. Water scarcity is another prime driver for treated wastewater reuse. This slide shows the increase in drought conditions over the last 6 years in the United States. The Western and Northern Plains states have had a particularly extensive increase in drought severity, but even the Eastern Seaboard has been experiencing more severe drought conditions. The duration of the drought in the West may be a result of global warming, and many scientists now consider much of the West to be experiencing not drought, which is a temporary condition, but rather true aridification, which is a permanent condition. Of course, a shift to arid conditions makes water conservation and reuse critically important. Population growth in Western areas adds further stress to water supplies for drinking water and irrigation. Please turn to slide 16. This slide shows how the costs for both water and wastewater treatment have escalated. Overall in the United States, the average cost increase for water and wastewater treatment has been 41% since 2001, with wastewater treatment costs increasing at a higher rate than freshwater costs. And even in Ohio, as an example, which has not historically been a water scarce region, the average annual municipal and water sewer costs have escalated to almost 2 times the rate of inflation, as shown in the graphs. More stringent drinking water and wastewater regulations have driven much of the increased cost in regions that have abundant water supplies. The requirement for higher quality effluent from water reclamation facilities makes water reuse more attractive, as little additional processing is required, depending on the ultimate use. It's not unusual to see treated wastewater effluent with lower turbidity, a measure of clarity, and organic content, that is purity, than the receiving stream. Please turn to slide 17. Reuse of treated wastewater is a natural outcome of the water cycle, whether it's intentional or not. This slide illustrates what we call de facto water reuse in watersheds in the United States. De facto water reuse results when treated wastewater is blended with river or lake water and becomes influent raw water for municipalities or industries. Many watersheds have as much as 1 to 5% of the raw water derived from treated wastewater, and some in Texas and other areas have more than 15%. This de facto percentage changes with the season, and during dry periods, there are locations in the United States where close to 100% of the raw water is made up of treated wastewater. This percentage is increasing as drought conditions reduce the amount of natural surface water. So why is this important? The following slide will show that when water is intentionally used to supplement drinking water supplies, treatment to extremely high quality is required. This practice will extend to watersheds with high de facto reuse as well, particularly as drinking water regulations become more stringent. So please turn now to slide 18. There's a paradigm shift that has occurred with municipal wastewater treatment. Utilities are beginning to look at wastewater not as a nuisance, but as a valuable resource. Also, municipalities are managing drinking water, wastewater, and stormwater on a holistic basis. This means that all sources of water, fresh water, either surface water or groundwater, brackish and salt water, rainwater, and wastewater must all be managed to provide the best value to all customers. And this management must be done in a sustainable manner, with the understanding that water is a finite, limited resource. This paradigm shift is reflected in the decision of the Leadership Council of the Water Environment Federation, WEF, to promote the use of the term Water Resource Recovery Facility, WRRF, in lieu of the traditional WWTP, wastewater treatment plant, or POTW. Please turn to slide 19. There are many valuable components of wastewater, including organics, which can be captured and converted to energy, such as methane and or electricity, or converted to more valuable organic forms, such as biodegradable plastics or other compounds. Nutrients, mainly nitrogen and phosphorus, which are required for plant and crop growth. Thermal energy is also a valuable component of wastewater, and metals and other inorganic chemicals can also have value. While there are many valuable resources in municipal wastewater, it's the water itself that's by far the most abundant portion, making up more than 99% of wastewater. Living sustainably means that water supplies must be protected and made available for generations to come. And the recovery of this water fraction from wastewater is an important step in achieving water sustainability. The US EPA states on their website that sustainability isn't just part of their work. It's a guiding influence for all of their work. Please turn now to slide 20. When treated wastewater is reused, the level of treatment depends on the intended use. Water to be used for toilet flushing or irrigation of non-food crops requires lower levels of treatment than water for food crop irrigation or for drinking. This slide shows several potable water reuse projects in the United States and the processing steps required. Most of these potable reuse projects involve the blending of treated wastewater with reservoir water, and aquifer recharge is also becoming more common. These projects all use a high degree of filtration, microfiltration and or ultrafiltration, disinfection, UV ultraviolet disinfection is most common, and reverse osmosis for dissolved salt removal. It's important to recognize that all these treatment processes are supplied by Evoqua Water Technologies. Turn now to slide 21. In summary, wastewater reuse/recycle can reduce freshwater costs by providing a high-quality water source that's tailored to the specific use. Internal reuse systems can reduce the burden on the final wastewater treatment plant. Recycle and reuse can also address plant production needs for processed water. Reduced use of local natural resources and lower discharge volumes of wastewater into surrounding lakes and rivers fosters a good industry-community relationship. And finally, wastewater reuse and recycle protects a valuable, limited natural resource, which supports an organization's sustainability goals. This now concludes our presentation. There's an appendix that follows that includes definitions of technical terms, along with some case studies.